Yeah, hi everyone. I hope most of you can hear me, right? Can you please quickly confirm if you can hear me? If there is any problem, please let me know. Okay, so everything is good, right? My screen is visible and I'm audible, right? Okay, so if everything is good, we can proceed further. Please confirm me quickly if things are good. So let's just start now. Those who are seeing me first time, let me quickly introduce myself. I'm Sachin. I'm co-founder and instructor at GoClasses. I have done my masters from IISc Bangalore, and after that I have worked at Amazon as an applied scientist. I've also achieved All India in 33 in GATE. Okay, so maybe let's start. So today's topic will be threads and scheduling, right? So which means that we are going to look at the threads and then we will look that how to schedule those threads and even how to schedule the processes. So today we are going to see threads and scheduling. Let me know if there is any problem in yesterday's session. Everything is fine, right? Okay. So let's just start now. Okay. Is there any problem in yesterday's session? Can you please tell me if there is some issue, or we can directly start? Okay, great. I think we can start, right? So today we are going to study threads and scheduling. So let's just first talk about the threads. So as I also briefed yesterday that in certain situations you might need some threads for a similar task, which means suppose you are on the word processor. I mean, this is just one example of the threads, but it is not the only example. In the sense that there is something that you want to leverage those threads just to make your system faster. So let's just see this after the slide. But for the similar task, maybe you want to write something. Maybe you want to type also. You want to do a spell checker also. So there could be many things that you want to do on this word file. So I mean word process. So you might be needing multiple threads, right? So since it is going to be a revision session, that's why I might not be spending too much time on the everything, but I will be focusing on the critical concepts only. Okay, so threads are about the concurrency and the parallelism, which means that if you are applying the threads, then if there is a only single core, then you can have the concurrent execution of those threads. Concurrent means you are running this thread and then you are running another thread. You cannot have a parallel execution. Obviously, I mean, how can you have the parallel execution if that is just a single that is just a single process, right? Okay, I think there is some issue in my screen. Let me just fix it. Okay, maybe I think it is better now, right? Just a second. Yeah, I think it is little better now. Great. So maybe I can do this. Yes. So let's now continue. So I was saying that if you are concerning about the threads, then these threads could be, you can run those threads in the parallel, or you can run these threads in the concurrent way also. So if it is just a single thread, right? If it is just a single thread, then you cannot run. If it is just a single CPU, then you cannot run in the parallel, because the using the single CPU, how can you run the parallel? So using the single CPU, you can have the concurrent execution. Similarly, if you are having multiple CPUs or multiple cores, then you can have the concurrent execution, right? So there could be a parallel execution or there could be a concurrent execution. It depends whether you are having a single core or you are having multiple cores, right? Great. So this is a single core, this is a multiple core. Now let's talk about the things that they share. So thread is basically for the process. If this process is having a single thread, then everything like this code, data, files and everything are shared for this thread. But let's suppose if there are multiple threads for this process, then I talked about this yesterday also. So there are few things that we have, which are the code, data, code and data are generally in the static area, which means they are generally in the read only memory, right? And the files that that this thread is using, so these are the few things that a process has, right? A few things that a process has, right? It has code, it has data and all. Now tell me, what are the things that you think that we might be sharing between the threads? What are the things that we might need to share? Any guesses? So if you are having multiple threads, then tell me, is it a good idea to share to have the separate code for everyone? Obviously no, because if there is one process, then it is having a one single code. So the code will be shared and the data will also be shared. Why? Because one thread might want to modify some global variable. Then is it a global variable of just a single thread, or this is a global variable of multiple threads? Obviously this is a global variable of all the threads, because this is just single process. In this process, if there are let's suppose two functions, fun1 and fun2, and I am running these two functions, fun1 and fun2, these two functions as in different threads. Let's suppose I am running this in thread t1, I am running this in thread t2, and there is a global variable, let's suppose int a. Now tell me, this a is shared or a is not shared? Obviously this a is shared, right? Since this age is shared, that is why I will say that I need to basically share the data, right? So we will be sharing the data. Okay. I'm just keeping my video to be little minimized so that you can see everything, right? I hope that is fine. Great. Now let's just continue. So basically you will be sharing the data. Data means the global variable or the static variables. Generally this data means this only, right? Global and static variables. Files means like whatever this process is using the files, like whatever number of the files. Let's suppose this is using some files, then obviously like these files will also be shared. You will not be copying the files, right? In the disk, in the hard disk, you will not be copying the files, and you won't say that this file is just related to this thread. Obviously that's not the good idea, right? I mean that's it's not just about good or bad, it is not even the idea to be considered, because that will be the wrong thing. Like you cannot copy the files. So that is why the files are also not I mean you cannot copy the files, right? So anyway, now continuing further about the registers and stack. So obviously this registers and stack had to be separate for every thread, because this thread might be doing some local operation that may need to store some values on some register. So that is why this registers, and similarly this thread might be having its own local variable, and those local variable are stored in the stack. So basically this thread and this thread must be having different registers in the stack. So register in the stack must be separate copy, else this code, data and the files will be the same copy. So in any thread. So this is the multi-threaded process. This is just a single threaded process. Okay. Now going further, this is about old process address space. Address space means the space that it is using, the total memory it is using. Now currently it might not be 100% clear that what is this code and static data and these kind of things. But once you go to something called as logical memory, okay, there is some term called logical memory, then it must be clear. What is logical memory? Let me just glimpse you for this logical memory. As a name suggests that it is logical. Logical means that it might not be the real memory, it is logical to have that memory, which means that that I will say that my program, okay, my program is having some memory that is from logically it is running from 0 to, let's suppose, ffff. Okay, well, logically it is going from 0 to ffff, which means this is just a logical memory which is a contiguous memory. Okay, you can say it is a contiguous memory also, contiguous memory. So it is just a logical memory, which is you can also say it is just a contiguous memory, and this need not to be the real memory, which means in reality this memory need not to be contiguous. right? So I'm just saying that I'm running from 0 to FFF, but in reality what do happen that you also know, right? I mean, what we do, we just divide whatever process is using, we just divide this into multiple pages, we store that into some physical different locations, some physical pages, right? And then we have the paging and all. So in reality that gets stored in different locations, but logically I'm saying it is a contiguous memory. So that's a good thing for the CPU and for the compiler also. Maybe we will talk about this logical memory later. So earlier my logical memory is looking like this, but now since we have multiple threads, now the logical memory will look like this since there are multiple threads, right? Great. Now I have the different stacks. Cool. So moving further, there are two type of threads. One is user level, another one is kernel level. And what is the similarity and difference between user level, kernel level? Let's just see this. User level threads are basically made by the function calls. I mean, if you are having some function call, or maybe you can say there are libraries which are at the user level. And if you are obviously, if you want to have the kernel level threads, then you have to have the support of operating system, and to have the support of operating system, you must be basically doing the kernel level threads, right? You must be making use of the system calls. So basically, if you are using the function call, there will be a user level thread. If you are using a system call, there will be a kernel level thread, like that, right? I mean, that's very simplistic form of putting it. There might be some complication, but at the end it boils down that for the user level thread, you do not need a system call, you do not need a operating system support. For the kernel level, you need a operating system support. That's why you need a system call also, right? Okay. Now every thread is having something called as PCB, right? PCB, or maybe some people like to call it TCB, which is thread control block. Thread control block. Okay, or maybe PCB. Every thread, maybe it is user level or it is kernel level, does not matter. Every thread needs TCB. So for the user level, if I just ask you that how to create those threads or how to initiate those threads, then there are some libraries that help us to initiate their threads, and similarly for the kernel level also there are some library that help us to initiate their threads, right? Now yeah, that is what you can read if you want from the Kelvin. I have taken this, so you, if you want, you can read. A thread library provides a programmer with an API for creating the managing threads. So there are libraries that help us to create or manage the threads, right? A second approach to implement a kernel level supported directly by the operating system. In this case, code and data structure for the library exist in the kernel space. So basically, there are libraries that help us to create the kernel level threads, and those libraries basically you make use of function calls. Sorry, system calls. Make use of system calls, right? Now there is, let's suppose there is some program which is, let's suppose P1, and that is having multiple threads. Now currently I am talking about the user level threads only. What is a user level thread? In those kind of threads, like kernel do not know like what is happening, right? I mean the OS do not have any visibility to the threads. So basically in these threads, let's suppose this is P1 which is having 3 user level threads, P2 which is having 2 user level threads, and P3 which is having just 1 thread, and which is a user level thread. But interestingly, or maybe unfortunately, for the kernel, this is just one process. There are not multiple threads, right? This is just a one process for the kernel. I mean, that's just a one process, which means, let's suppose this P1, is having 3 threads, T1, T2 and T3. Let's suppose, okay, this P1 is having 3 threads, maybe T11, T12, T13. This P2 is having also, let's suppose, 3 threads or maybe 2 threads, maybe I can say T21, T22. Okay, and let's suppose this P3 is also one more process which is just having 1 thread, which is maybe, let's suppose, T31. Suppose these are the three threads, and all threads are user level threads. All threads are user level threads, right? So suppose all threads are user level threads, and now in this case, what we want to do, we want to just check that what is the benefit, or maybe like how the this user level threads are visible to the maybe I can say visible to the kernel, right? Let's just see this. So these are some user level threads. Now what I want to check, if I run these programs on some operating system, on some CPU, okay, with the help of operating system. Let's suppose I am running this program with the help of operating system on some CPU. Now this CPU doesn't know whether there is a multiple threads or this is just a one program, right? I mean in this P1 there are multiple threads, but the CPU doesn't know this. So in this P1 there are 3 threads, that is okay, but CPU doesn't know this, which means if you are scheduling this P1, Now which thread you want to schedule, like I mean CPU doesn't have any control, that's called user level threads, user level schedulers, user level schedulers, that will say that okay, let me schedule this T11, let me schedule this T12, something like this, right? Now in this kernel or maybe kernel level scheduler does not have, or operating system scheduler does not have any control on this, right? Now consider the scenario where I do have two CPUs, okay, let's suppose this is CPU 0, this is CPU 1, there are two CPUs and there is just a one process that is having three or maybe just two, let's suppose T1 and T2 user level threads, user level threads. Now tell me, if I am running this P1 on some CPU 0, okay, on this CPU, then let's suppose that currently I am running T1 only. Now tell me, at the same time, can I run the T2 on the CPU 1? So my question is that if there is a program that is having multiple user level threads, okay, currently I am only talking about the user level threads, then in this case if T1 is running on this CPU 0, then T2 can this T2 can, my question is that can T2 run on CPU 1? This is my question. Let me know. What do you think? Can this okay, yeah, answer is no. Why? Because for the CPU, right, I mean for this operating system, I mean who runs this this T1 on the CPU? Operating system, right? With the help of operating system I'm running. So for this operating system, this P1 is just one process, there are no multiple threads, so operating system cannot take advantage of this user level threads, right? I hope you are getting. So see this diagram very carefully. Here for the operating system, this is just a one process, right? But when I go to the kernel level threads, then this diagram will be something different. Okay, if I just show you that diagram, this was the user level thread, and if I just show you the diagram for the kernel level thread quickly, then this is the kernel level thread diagram. I will come to this little later, but I'm just telling you in advance, maybe some ahead of time. I'm telling you that when I go to the kernel level, then the diagram will look something like this, right? These are the kernel level threads. Okay, so I will talk about this, but these are the kernel level threads. Can you spot the difference? The difference is that here the operating system knows that okay, these are the three threads. So basically the operating system can run this on some CPU, this on another CPU, like that. So basically operating system scheduler can make use of these three threads. So for the operating system scheduler, these are 1 2 3 4 5 6 7, these are something like the 7 processes. Okay, but these are just the three processes. So that's the difference between kernel level threads and the user level threads, right? I mean for the user level thread, operating system does not know anything. Yes, that is correct. Yes, Alokam. Because the operating system does not know. Yeah, excellent answers from everyone. So I'm very glad that everyone is getting everything right. Okay, great. Now let's move further. So this operating system, this user level thread does not take advantage of the operating system scheduling. User level threads are small and fast, but that's the best advantage of the user level threads. These are small and fast. Why? Can anyone tell me why it is fast? Because it does not have system call, does not need system call. So system call means it is very cumbersome to have a system call and do something, because system call takes time, because you switch the context basically, I mean whatever is running for your process. I mean in case of system call, you go to the operating system code, which means you run the operating system code. Basically it is just context switching. I mean whenever you are running some process P1 and on the system call you need to run operating system code, that will create the threads and then it will return to you. So basically it is not very fast. I mean it is generally it takes some time. For the user perspective, you might think that okay, it is just a microsecond of different, but that's okay. I mean microsecond or millisecond, we should not measure in terms of our time. I mean for us maybe 1 hour is very less, right? It is not like that. It is basically with respect to the CPU is very fast, and if I'm even wasting a microsecond, it might not be a worth to do it. Okay, so there are some libraries called pthread and all. These help us to create the user level threads. So what is the advantage of user level threads? These are fast. That's the only advantage, because they do not make use of the system call. So user level thread operation can be 10 to 100 times faster than kernel level thread. Okay, so yeah, Now, these user level threads are basically called many to one mapping. That's very, very interesting. What does this many to one mapping mean? Can you see my screen? Okay. Maybe let me just adjust it a little bit. Just a second. Yeah, I hope now everything is fine, right? Great. So I hope you can see my screen now. So let's just see that what does many to one means. What does this many to one means? It says that you are having different user level threads. Many means there are many user level threads, right? Many user level threads, and there is only one kernel level threads. Kernel level threads. This is the one means kernel level thread. There is for the kernel this is just a one thread, or for the operating system this is just a one thread. That is why these user level threads are also called many to one threads. Many user level threads map to single kernel thread. See here, many means many used for the user level thread, and one is used for the kernel level thread. So many user level threads are mapping to single kernel level thread used on the system that do not support the kernel threads, right? These kind of threading system, let's suppose my operating system is not supporting me for the kernel threads, so these kind of systems can be used for the for the things which are basically not making use of the kernel threads, right? Okay, so user level threads is a thread that OS does not know about it, right? That's a very important point, that OS does not know about these threads, but these are the fast. OS only knows about the process containing these threads. So only one process OS knows. OS only schedule the process, not the thread within the process. That's very important points. All the points are very nice. They may ask that that in the MSQ. Okay, I mean very simple MSQ could be something like this. Which of the following is true, right? They may ask which of the following is or are true. So these are the let's suppose three options. OS only schedules the process, not the programmer uses the threaded like, okay. I mean they may ask like which of the following are true. Then if it is a MSQ question, then you will say that A, B, C, D all are true, right? All are true. Something like this. Let me know if that is fine to everyone. Great. So user level thread means that as I again said, like only OS knows only about the current process, not about the threads. But this is basically what the kernel sees. I mean, if you are having multiple threads, but kernel does not see multiple threads. That's the thing, right? Kernel only sees that okay, this is one process. Inside this, you are having multiple threads. Kernel doesn't know about it, right? Great. Now let's just solve this question. What is the major advantage and major disadvantage of the user level thread? Can anyone tell me? What is the advantage? Advantage is that they are fast. As I said, this is the best advantage. No context switch and all, right? And what is the disadvantage? That OS does not know about these threads. So yeah, there are advantage also, there are disadvantage also, right? Okay. Now let's move further. Let's solve this question. So what they are saying is that what is the biggest advantage of implementing threads in the user space, right? So what is the biggest advantage of implementing thread in the user space, and what is the disadvantage? I think the answer is same. The biggest advantage is the efficiency. That's the advantage, and no traps to the kernel are needed to switch the threads. So basically kernel involvement is not there, so that's why these threads are fast. The ability of having their own scheduler can also be important advantage of their certain application. The biggest disadvantage is that one thread blocks the entire process block. So that's very important. See, let's suppose that this thread, okay, suppose there are multiple threads that I have, and this thread, let's suppose this thread is waiting for some IO, okay, waiting for IO. Then OS does not know that okay, there could be multiple threads also in this. So OS says that okay, this process, for the OS it is like this process is waiting for the IO. So OS will block the entire process, not just one thread. So that's also one of the major disadvantage, right? OS will just block the entire thread, no, not just a one. OS will block the entire process, not just a one thread. Let me know if that is clear to everyone. Yes. So great. Yeah. Now let's just move to the kernel level threads. Kernel level threads are also similar. It is just that kernel have the visibility to these threads, right? Kernel have the visibilities. So like these are few points about the kernel level threads, and all the points are almost same that I talked like again and again. So OS now manages the threads, right? Kernel threads are cheaper than the processes. Yeah, in compared to the processes, they're cheaper but costlier than the user threads. Which means, like if you say that that I like if you have two options, maybe maybe kernel level thread is one option. Okay, so I let's say that this is 1, this is 2, this is 3. Okay, and I want to arrange them in the order of costly. I mean, which one is most costly? One is user level thread. I mean, creating user level. User level thread means creating a user level thread. Okay, so let me write like this. So now tell me what is the correct order. Creating a user level thread. Second one is creating a kernel level thread. And third one is creating a new process, maybe using fork exec, right? Which one you think is most costlier then? Can you arrange them in the order of costly? Can I say that one is greatest, then second, then third? Is this the correct order? Or maybe let's suppose this is A, maybe the second one is greater, and then third, and then one. This is B, something like this, right? Maybe third one is greatest, then second one, then first one. This is C. Which one is the answer? A, B, or C? Can anyone tell me the answer? Let me know quickly. What should be the correct answer? I think answer is C, right? Yes, 3 to 1. Because creating, why creating a new process is costlier than the kernel level threads? Can anyone tell me? Why this third is greatest? Third is, why this third is greater than 2? Yeah, between second and one, you know the answer because of system call, right? Because of system call involvement, system calls. But why this is the relation between third and second? Because the kernel level threads, if you're using the threads, then you do not need to copy the entire space. Maybe some of the things you need to copy, right? You do not need to copy the entire space in the kernel level thread, right? You do not need to copy data and code, and there are many other things, right? Open files. So anyway, so data, code, these things you do not need to copy in case of second. In case of third, you need to copy all of the thing. So that's why the third is most costlier, and then the second, and then this first, right? So I hope you understood. Okay, so now let's just continue. So this is the summary, the thread, a single execution within the process and all. So this is a summary. I hope everyone agree with this, that thread is a single execution stream within a process. Switching between a user level thread is faster between the kernel level thread, since a context switch is not required. Yeah, switching is also one criteria, that if you want to switch between user level thread and between two user level threads, and switching between two kernel level threads, then switching between two kernel level threads is just like switching between two processes, almost just like that, right? Because for the kernel, these are just a different processes. User level thread may result in the kernel making poor scheduling decision. Yes, everyone agree with this, because let's suppose there are two CPUs, and if there is only just one process I am running, but it is having multiple user level threads, then also I cannot run these two threads on the on two different CPUs, right? So that's why it may lead to the poor scheduling decision. Okay. Now for the performance, as I said, like this kernel threads are basically, let's suppose this fork is taking 251 microsecond, okay, in some system, then the kernel level threads are just taking 94 microsecond, which is 2.5 5 times faster than the creating a process. But the user level threads are extremely cheap, they are just taking 4.5 microseconds, something like this, which is 20 times faster. Okay. Fork versus threads, so which one is more heavy? Obviously fork, right? Because we need to copy the whole address space. why we should prefer threads than fork in the similar task? Why we should prefer thread? Because they're cheaper, right? Threads are cheaper. Okay. Now let's just do these questions which are asking true or false. So just tell me if this is true or this is false, something like this. Okay. So these questions are true false question. True, false. Let me know which one is true, which one is false. The OS provides illusion to each thread that it has its own address space. Is this true? Do OS says that every thread is having its own address space? No, right? Address space means complete thing, data, code, everything should be separate. Do OS says to the threads that okay, everyone is having their own address space? Answer is no, right? False. Everyone understood why it is false? Because OS does not say that everyone is having their own address space. What about this one? With okay, don't go with these numberings, right? These numberings are just some random numbers. Okay, so with kernel level threads, multiple threads from the same process can be scheduled on multiple CPUs simultaneously. Let me know if this is true. With the kernel level thread, can you do it? Yes, I think we can do it, right? With a kernel level thread, we can definitely do it. So the answer is yes. With a user level thread, we cannot do it, right? Okay. So yes, this is true, this is false. See the reasoning. Each process has its own address space, but the thread in the same address space share the address space, right? I mean, they share some code and the heap and all, right? Yes. Their stack is different, but they share the code, data, and heap. With kernel level threads, multiple threads are from the same process. Okay, so here this is true that you can schedule if this process is having, let's suppose 3 kernel level threads and there are 3 CPUs, right? Then you can schedule these on the different CPU because that is visible to the OS. Yes, this is the benefit of the kernel level. True, it is called true thread support from the operating system, and we could not do it with the user level threads. Great. Now let's just solve this question. Tell me if it is true or false. If a user level thread, so tell me it is true or false. If a user level thread is blocked for IO operation, then kernel of OS will perform the context switching to run another user level thread which is not blocked. If a user level thread is blocked for the IO operation, then kernel of the operating system will perform context switch to run another user level thread which is not blocked. Is it true? If one thread is blocked, then the operating system will schedule the another thread if it is a user level thread. False, right? This is false. So great. This is false. Let's move further. So let's just answer this question. What they're asking is that many to one is the most efficient model of the multi-level. Okay, this is again true false. Many to one means there are many user level threads and one kernel level threads, right? These are many user level threads and only one kernel level thread. So what they're asking is that many to one is the most efficient model of multi-threading because it allows several threads to be assigned to different processes in the multiprocessor computer system. Most efficient model of multi-threading because it allows several threads to be assigned to the different process. Can you allow the several process to the different process? This is also false, right? Yeah, Mayuk is asking to kernel. It is a, yeah, that is true, Mayuk. Yes, Alokam. Yeah, you are saying correctly. This is also false. Great. Let's move further. So I think these were the answers of the previous questions. Okay, both are false basically. Now let's just answer this question. Tell me whether this is true or false. Okay. So is this true or false? In a multi-threaded processing with kernel level threads, the various threads associated with the single process must share the common thread state. With the kernel level threads, the various threads. So if all are blocked, if one is blocked, then all must be blocked. They are saying if one is blocked, then all must be blocked. If one is running, then all must be running. Should it be true or it should be false in the kernel level? So this is false, right? Yes, Deeptanshu, that's correct. So that's false. I mean, they do not share. For the kernel level, they do not share. Yeah, if this could have been the user level, then they do share, right? Okay. So now let's just answer this question also. In a multi-level threading, the kernel level threads, the various threads associated with the single process must share the common thread. Okay, sorry. Yeah, that is false. Now, so let's just answer this, whether it is true or false. Can you see the question correctly? In a multi-threaded processing, the various threads associated with the single process share the common user stack. Do they say share the common user stack? No, right? So that's also false. Okay. Now let's do this question, which is very interesting question. Let me just copy this question on the next slide, and let's try to do this question. What they are saying is that they are saying, suppose there are three processes exist in the system. The described table below. Okay, these are the three. Suppose the system uses the preemptive round robin scheduling, and T11 is running, and when the quantum expires. So they are saying T11 was running. Now, if threads are implemented completely at the user level with no support from the operating system, then which thread possibly we execute at the beginning of the next quantum? So options are, this is A. So these are the options, right? So let me write the options here. Let me know what is the answer. Sorry. So let's suppose this is A, this is B, this is C, this is D. So they are saying that if you are currently running T11, then once this T11 is finished, okay, after the timer quantum expire, then which one be possibly be running? Let's suppose this is a MSQ question. Actually, this question is from goclass's mock test only. Has anyone attempted mock 2? This is a question of mock 2. Okay, so let me know what is the answer. See, they are saying that T11 was running and the quantum got expired. Now, which one is likely to run? Possibly execute. Can you execute T12? Can you execute T12? If T11 was running, it means that for the kernel, this was just one process. Then it cannot schedule any other thread within this, because for the kernel, this whole thing is just one process. So that's why it may run this, may run this, may run this. So maybe T12, maybe T12, maybe T22, maybe T23. But anything which is T12 or T13 cannot run, right? T12 or T13 cannot run if T11 just got finished. Okay, so I hope you understood this question. Let me know if there is any doubt. So that's very nice question. That for the kernel there is no view that what it should run. I mean, there is no view of threads within the process. So that's why it will run another process. Within the another process, it may run anything. It will depend that which one you are mapping as a user level scheduler, right? User level scheduler will map level scheduler will map one of this, either T21 or T22 to one kernel level thread, right? So answer is B, C, D. Great. Now let's just see the second part of this question. What they are saying now? They are saying if threads are supported, okay, So let's just see the second part of this, the same question. They are saying if threads are supported by the operating system, right? Now, if the threads are supported by the operating system, then which one might run? So now they are saying if threads are supported with the operating system. So what should be the answer here? Let's suppose that these are the only options that I have. So can you tell me what should be the answer? If threads are supported by the operating system, then which one can you run? Can you run T12? Can you run T13? Can you run T21? Can you run T31? Okay, let's suppose this is A, B, C, D. Maybe let's suppose E also, which is T11. Which one is the answer? Which one is the correct answer? Let's suppose this is again MSQ. Let me know quickly. See, if threads are supported by the operating system, then apart from this T11, it can run anything, right? Apart from the T11, T11 cannot run. Apart from this, it can run this, can run this, can run this, can run this, right? So anything except this T11. So answer is anything except this T11. Now let's just continue one more part of this question. What they are saying next is this. Okay. Now suppose that they are saying that let's just consider the same scenario, and in this case they are saying like instead of one CPU you have the two CPUs. Okay. How does the answer change if there are two processes? If there are two processes, then how does the answer change? That's what they are asking. Answer to the previous ones. For the user level thread, if T11 is running, so I don't think like the answer will change in any way, because kernel is not aware about these threads. So kernel will anyway like run either this process or this process, right? And for the kernel level threads, since the kernel is aware about all of this, then kernel will not run this because the quantum has just got expired. So kernel will either run this. So answer will not change in this case. Either it is either it is one process or two processes, right? So it actually doesn't change. In the first case, the kernel will not know about the user threads, so no choices can be made. In the second case, the kernel will have the full knowledge of the user threads and will make the same decision, of course, realizing that kernel should not run the same thread simultaneously on the multiple process. Okay. So I hope you are getting the point. Now let's just do this question. What they are asking is this: whether these are true or false. Okay, sorry, the answer is written here, but yeah. So let's just see these questions. A blocking thread blocks all the threads in the process. A blocking kernel scheduled thread blocks all the threads in the process. Kernel scheduled threads. A one blocking kernel scheduled thread can block all the threads. Is this true or false? So the answer is false, right? It is not true. Threads are cheaper to the context switch than process. Yes, that is true. I mean, because you do not need to save a lot of the things. If you want to do some context switch, then you do not need to save a lot of the things, just like a process. A blocking user level thread can block the process. Yes, that is also true. If one thread is blocked, then whole process is blocked if it is user level, right? Okay, great. Let's move further. Yeah, false, true, true. So now let's just answer these questions. Maybe just a second. I hope this is visible to everyone, right? So tell me whether these are true or false. Do not look at the answers. What they are saying, let's just see. In an operating system environment, that operates with the user level threads only, no kernel level threads. The various threads associated with the single process all share the same common context, including the common PC. Tell me, do they share common PC, program counter, or the registers are different? If you are answering, Deeptansu or Harish, if you are answering, just answer something like this: 38 true, 39 false, something like this. Okay, answer with the number, so that I get to know that to which you are answering. So obviously this is false. Why? Because if this is any thread, then they must be having different program counter, obviously, right? I mean their registers are different. In an operating system environment, this is also false. I mean they can, including the common PC. So common PC cannot have either it is user level thread or kernel level thread. The different threads associated with a single process all share the single processor context. Context means that is the value of the processor status word is same for all such threads. Do they share the same context? Okay, what do you think? Just let me know quickly. So what do they mean by the context, right? Context means everything. I mean the whole thing that we have, which means like your code, data, and everything, stack and all, right? So the whole thing they share the everything is same in all the in all the threads. So answer is false. No, everything is not same in all the threads, right? Now let's just see this. Thread creation take more time than the process creation. This is also false. Thread creation take even the lesser time. Each thread associated with a single process has exclusive ownership of any files that is open. No, it do not have exclusive ownership. Like files are shared. As I said, code, data, these things are separate. But I mean the files is files. Sorry, code data. These code data files. These things are shared, and stack and register, these things are separate. So if two threads has opened the same file, they do not open they do not own the like separate ownership, which means like it is not like that I am the owner of this file and you have the another file of the same copy and you have the separate ownership. So they do not have exclusive ownership of any file. So this is also false. Each thread associated with a single process has a separate text. They have the separate code? Let me know. No, right? I mean the code is also shared. So that's why this is also false. So I think everything is false, right? Yeah, everything is false. Okay. So now let's just do this question. This question I have taken from University of Waterloo. Okay. So let's see what they are trying to ask. I hope the question is visible to everyone. So what they are asking is that suppose two long running process P1 and P2 are running in a system. Neither program performs the system call that might cause to block, and okay, so none of this program. So there are two programs P1 and P2 that are running in a system, and none of this program perform a system call that might cause it to block. So neither it is performing a system call, I mean blocking call, nor it is performing a blocking call. And there are no other process in the system. P1 has two threads and P2 has one thread. So P1 is having two threads, T1, let's suppose T1 T11 T12 or whatever, right? Or maybe it is having just one thread T. Let's suppose it is having two threads T1 and T2. It is having just one thread, which is let's suppose T5 or T3, something like this, right? Now what they are saying, that what percentage of CPU time will P1 get if the threads are kernel thread? Okay, suppose there is a fair scheduling, then in that scheduling what percentage of time? Fair scheduling means everyone is getting the let's suppose it is a round robin. Okay, suppose it is a round robin. They are long running process. Round running means let's suppose they are running for the infinite time and it is a round robin. So what do you think? For the kernel level threads, it is actually for the kernel. The T1 is different process, something like this. T2 is different process. T3 is different process. So kernel will give two times more time to this P1 than this P2, which means this T1 will run, then T2 will run, then T3 will run. That's what will happen. Okay. If there are kernel threads, right? So T1 will run and then T2 might run and then T3 might run. So basically, the thing is that for the kernel, these three are different processes. So it will give the equal amount of time to these threads. If it is kernel level thread, right? Kernel level. Now what if it is user level? For the user level, it will be something like this. Either it will be giving a chance to T1 or T2 and then it will be giving a chance to T3, right? And at the next time, maybe it can give a chance to T2 and then it will be giving the chance to T3. Basically, it will be giving equal chance to P1 and P2. So that's why if it is user level thread, then both are getting 50% P1 and P2. But if it is kernel level thread, then P1 is getting out of this 3 time slots, P1 is getting 2 time slots, which means it is getting basically 66.6%. Okay, it is getting 2 by 3 time of the CPU in the kernel level thread, but in the user level thread it is just getting 50% time. Is this understood to everyone? Okay, so I hope that is fine. Now let's move further. Yeah, so it is 66% and it is 50%, right? Okay. Now let's solve some of the gate questions so that we get more confidence. Let's see what these questions are saying. Just spend some time in solving these questions. Consider the following statement with respect to the user level thread and the kernel supported threads. Kernel switch is faster with the kernel supported threads. Context switch is faster. Is this true? If this is kernel supported threads, then context switch is faster. For a user level thread, a system call can block an entire process. Kernel supported threads can be scheduled independently. User level threads are transparent to kernel. So which one is true and which one is false? Just spend some time and let me know what is the answer. Okay, T.S. Karthikeyan is saying B is the answer. Okay, so he's saying only second and fourth is the answer. This one is first is false, I think, right? This is what you are saying. Context switch is faster with the kernel supported threads. Yes, first is false. So if you compare between user level threads context switching, level thread context switch versus kernel level thread context switch. If you compare between these two, so user level thread context switch is very easy, in the sense that let's suppose this is some CPU which is running some program P1. Now in this program, let's suppose it is running for this much time. Okay, P1 is running for this much time. Now you might be running some thread T1, and all of the sudden the user level scheduler wants to schedule to T2. So will there be a context switch here? Am I interrupting CPU to do the context switch, or I'm doing it on my own level? So I'm doing it on my own level, right? So this is the user level scheduler that will do it. So that's why this is faster. If this is user level context switch, then it is faster. Right? I hope that is clear to everyone. Let me know if there is any doubt. Okay. Now, user level context switch is faster compared to kernel level context switch, so that's why this is false. What about this one? For the user level threads, system call can block an entire process. Yes, that is true, right? One thread is blocked, entire process is blocked. Kernel supported threads can be scheduled independently. Yes, that is also true. User level threads are transparent to kernel. Okay. So what do you think about the fourth option? So what does this transparent mean? Transparent mean like I think here the transparent mean that this kernel is not aware about the user level thread. Okay, so just interpret this statement just like this, that kernel transparent. If the transparent mean that I'm not sure about the English. Transparent here mean that kernel is aware about the user level thread or do not aware about the user level thread. User level threads are transparent to kernel. So what do you think is the answer? Transparent. So by the way, what does this transparent mean? I think the transparent mean that kernel is not aware about the user level thread, right? So maybe let me just put a blog that is available on the Stack Overflow. So what does this transparent mean? Let's just see. So I've copied that from the Stack Overflow. They are saying that kernel level threads are not transparent to the kernel, but the user level threads are transparent, because you yourself said that user level threads are managed by the user level library, and what happens is the user level threads can get assigned to one or many kernel level threads. Okay, about these kernel level threads, the kernel keep track of are not transparent to the kernel, but it does not know which user level threads uh, we have got assigned. Okay. So only these kernel threads and how many, but it does not know which user threads have got assigned onto these kernel threads and how many. Say if 5 user threads are assigned to one kernel thread and 4 user threads are assigned to another kernel thread. So they are saying, suppose that there are 5 user threads, 2, 3, 4, 5, okay, 5 user threads T1 to T5 are assigned to just one kernel thread, which means that there is one kernel thread that is responsible to running these 5 user level threads, which means if it is running, then then either you run T1, either you run T2, or maybe T5. Similarly, let's suppose there are some other let's suppose user level thread. Let me just call them as U1 to U4, and that are mapped to another kernel level thread, that is K2. Now what they are saying is that the kernel sees these two kernel threads. So for the kernel, there are only two kernel threads requesting execution, and does not know that there are altogether 9 threads, but it just knows that the program called user level application is or are using the two kernel threads. So basically, if you are having two kernel threads, then it just knows that there are two kernel threads. It does not know that in total there are 9 user threads. Okay. So I think here the transparent only mean that kernel is not aware about the user level thread. So if that's the meaning, then it is also true. Okay, if the kernel is not aware about the user level threads, right? So if the transparent mean that kernel is not aware of the user level thread, that's why the A is the answer. If the transparent mean this user level, yeah, A is the answer. They are also saying user level threads are transparent to the kernel. In case of computing, transparent mean the functioning without being aware. See, yeah, transparent, if the transparent mean without being aware, then this is the answer, right? So it is just a bit of English that we need to take care. Okay, anyway, the concept should be clear, otherwise don't worry about these kind of English. I mean, you may get it right, you may get it wrong, depending on what you interpret in the examination. So don't worry about it. Okay. Okay, moving further, can you solve this question? Consider the following statement about the user level thread and the kernel level thread. Which one of the following is false? Context switch time is longer for the kernel level threads than a user level thread. What do you think? Context switch time is longer for the kernel level thread. I think that is true, right? Seems true. User level threads do not need any hardware support. Yeah, I mean, why will they need? Because hardware means basically in the hardware there is there is a bit called mode bit. In the CPU itself there is in fact a flip flop. Okay, that is called mode bit. That is either 0 or 1. It depends on whether you are running in the kernel mode or you are running in the user mode. So you do not need any mode bit to change. So that's why it is also true. What about other options? Related kernel level threads can be scheduled on a different process in a multi-process system. Related kernel level schedule on a different process. Yeah, that is also true. Blocking one kernel thread block all the related threads. That is false, right? So that's why D is the correct answer. Have you understood this? Yes. So yeah, great. Everyone is giving me the correct answer. Now let's just solve this question. Can you tell me which one is the correct answer here? A thread is usually defined as a lightweight process because an operating system maintains a smaller data structure for a thread than a process. In the relation to this, which of the following is or are correct? OS maintains only scheduling and accounting information for each thread. OS maintains only scheduling and the accounting information for each thread. OS maintains only CPU registers for each thread. OS does not maintain virtual memory state for each thread. So what is the correct answer? Just think about it and let me know. They are asking about the correct option, right? Maintains a smaller data structure for the thread than the process. So basically, the bookkeeping or the accounting information, accounting or bookkeeping both are same. Bookkeeping means like the information that you need to save for the thread, which means what is the current program counter, stack pointer, these values. Okay, this is called bookkeeping, which is in the TCB. I mean, they are talking about TCB and the PCB. So the information that is getting stored in the TCB, right? They are saying the information that is getting stored in the TCB is basically the smaller data structure. Here it means the TCB, thread control block, right? Versus PCB. So PCB might be having many things, but TCB might be, this thread control block might be just storing few of the things, and then it will say for rest of the things contact PCB. Okay, they might be having just a pointer to contact PCB, right? So OS maintains only scheduling and accounting information for each thread. Is this true? Accounting means bookkeeping. I mean, what is the register value and all. So I think that is true, right? I mean, they do not need to maintain any other thing that that they have to maintain for the process probably, right? Where is the code? Where is the data? I mean, this information is not needed for the TCB. Yes, for the PCB, there are many other information like where is the page table. Like PCB will be having where is the page table, right? Which files are open, something like this, right? Which all files are open, and there are many things that PCB might be maintaining. But for the TCB, just maintain the scheduling. I mean, have like it is a turn for this particular thread or not, and that is not in the TCB. That is in the queues. Okay, these are in the queues. I mean, depending on the scheduling that you have, and accounting information that is in the TCB. So that is true. OS maintain only CPU registers for each threads. Yes. So only CPU. So in the bookkeeping, they only maintain the CPU registers. Like what is the PC value and what is the stack pointer value, like this. In the TCB, they only maintain these things. Okay. For each thread, there are different stack pointers. There are different program counter. There are different registers like that. So it only maintain in the TCB. You only maintain this. OS means this TCB and PCB both are in the OS memory. Okay. TCB, which is thread control block, and PCB, which is program control block, they both are in the operating system memory. Okay, so OS maintains this TCB, and inside this TCB you only maintain the CPU registers basically. Okay, OS maintain only CPU register for each thread. So that it is also true. This is also true. OS does not maintain virtual memory state for each thread. I think that is false. Virtual memory state means like where is the stack pointer and all. Like I mean, what is the state of the virtual memory that we have? So it is saying does not maintain. So I think this is false. OS does not maintain a separate stack for each thread. Is this true or false? OS does not maintain. OS actually maintain, right? Okay. Sorry, they are saying which of the following is the correct option. OS does not maintain the virtual memory state for each thread. Virtual memory state, what does this virtual memory state means? I think since the address space is common, only the registers are different, right? See, sorry, I misinterpreted this question, I think. Okay, see here what they're saying. The C option is saying OS does not maintain the virtual memory state. Virtual memory state means that the logical address space. Okay, so logical address, the entire logical address space. So OS does not maintain this, then answer is I think true. I mean this should be true because OS does not maintain the entire logical address space for each thread. Yes, Harish, that is correct. So that is true, but sorry, this A and B I think should be false. Let me reread it. OS maintains only scheduling and accounting information. Accounting information means that what are the PC values and all. Okay, let me see what does this accounting information mean for them. C is the correct answer. Many of you would not agree at first, so let me explain. OS on the per thread basis maintain only two things: CPU register state and the stack space. It does not maintain anything else for the individual thread. Code segment and the global variables are shared. Even TLB and the page tables are also shared since they belong to the same process. Okay, so option A is saying that only maintains scheduling and the accounting information. So would have been correct if only word will not there. It not only maintains the register state but also the stack space. Accounting information means I'm not 100% sure. So they are saying that here the accounting information means that only the registers. Okay, I think they should be little bit clear. Instead of this accounting information, they should be very clear what does this mean according to me. So if it is only register, then this is false, right? If it is the register and stack both, then it must be true. But if it is only register, then it must be false. OS maintain only registers. Okay, so they are saying only registers. Yeah, so that's also false. I mean, the stack for the they also maintain the stack area, like from where we are starting the stack and stack addresses of the stack. So registers and stack both are maintained. So that's why this is also false. OS does not maintain a separate stack. Okay, does not maintain that is false, right? So basically, OS maintains. They are also saying OS maintains two things. For every thread. One is separate stacks. Okay, so here the accounting information means only register, so that's why it is false. Okay, moving further. So let's do this question. What they are asking, the which of the following is false? Can you solve this question? User level threads are not scheduled by kernel. This is true or false? User level threads are not scheduled by kernel. That is true, right? I mean, user level threads are not basically scheduled by kernel. Kernel only schedule the process, and the user level scheduler schedule those threads. When a user level thread is blocked, all the threads of its process is blocked. So that is also true. This has been asked many times, right? This particular statement. Context switch between the user level thread is faster. Yeah, that is also true, right? That has also been asked in one of the previous PYQ. Kernel level threads cannot share the code segment. No, they share, right? That is false. So I think D is the correct answer. Okay, D is the answer, right? Now let us start with the new topic, which is scheduling, right? So basically, we are just going to do revision. We are not going to do the thorough theoretical understanding, but I will just pinpoint few of the theoretical understanding, and then we will directly go to the questions. Okay. So basically, scheduling means scheduling a thread or a process. Okay, could be anything. When I am saying thread, it is basically kernel thread. Which means user level scheduling is not like we are not interested in the user level scheduling. This scheduling is at the kernel level. I mean, what OS doing? OS scheduling, or maybe the CPU scheduling, right? So this is basically what does OS do? Okay, that scheduling, not the scheduling that user is doing. Okay, so let's see different states in which a program can be. So initially when you write the program, then it is we call it a new, like the program is currently in the new state, and then you load this program and then we call this program is in the, can anyone tell me which state? It's called it in the ready state, right? And then what you do, once you load this program, so that is called loading of the program in the main memory. Now it is in the main memory, right? Okay, so can anyone tell me first that how to load that program? So that is done by loading a program. Yesterday we have seen that how to load a program, using which system call we do it? Anyone? Using which system call we are doing it? We do it using fork exec. In the Linux based system at least we do like this, right? Okay, now that from this ready, then what can happen? That program can go to some state called running, right? I mean you may run this program, that is basically called scheduling. I mean this is loading and then you can call this as a scheduling. I mean you can schedule this program, and while it is running you may say that okay, maybe because of some event, maybe you can say maybe it wants to wait for the child. Okay, maybe the program wants to wait for the child. Maybe the program is having some sleep, okay, sleep system call, or maybe it is basically doing some IO operation. I mean it could be anything, right? IO operation or something like this. And then I will say that why to waste the CPU time, let's just move it to the block state. And after this block state I can say okay, it can move to the ready state whenever this when it can go, whenever sleep, wait or IO is complete. Right? So this is one process diagram, and then you can say from this running, if the running is finished, then it need not to go to the blocking state only. It may say that okay, let's just move it to the some state called exit or termination, right? Terminate. That is done using the exit system call. So there is a system call called exit. So everything is happening using a system call only, right? Exit system call, and that is I mean either a system call or some interrupt. That ready to running, maybe using the timer interrupt, right? I mean the timer is triggered and maybe using the timer interrupt. You're doing this. Everything is because of the some interrupt or I mean hardware interrupt or software interrupt. From running to block, maybe any of this interrupt has been arised. Maybe the IO operation, maybe the IO hardware interrupt, maybe the sleep, which is a software interrupt or the system call. Maybe this is also software interrupt or system call, right? These are the system calls. This is, let's suppose, the hardware interrupt, maybe the software interrupt also, but any kind of interrupt, right? IO operation could be the software interrupt also. Maybe the printf is an IO operation, which is a software interrupt, which means a system call only, right? Okay, so this is the process diagram. Let me know if that is clear to everyone. Yes, Deeptanshu, that was the fork and exit idea. Is it clear to everyone? Now tell me, like if that's the diagram that I have, now tell me, can I have in this diagram, can I have some state which is from block to running? Can I say that it was blocked, then eventually it is running? So generally it doesn't happen. Okay, I mean if it is blocked, then I will say okay, once it is complete, then I will say it is going to the ready state. Block to running, these kind of states are not possible. I mean these kind of transitions are not possible. Now if it is running, then can it directly go to ready state? Okay, I mean it need not to be the block state, which means that it is running and suddenly I say that okay, even though you do not want to block yourself, even though you do not want to, you do not issue any IO operation or maybe any sleep or maybe any wait, still I am saying that go to just leave out this running, maybe just go to the ready state. Can I say something like this? I can say something like this, and that is called preemptive scheduling. That is called preemptive scheduling. Just using this one transition, the scheduling becomes preemptive. Okay, and that is again using the timer get expired. Okay, maybe the timer is expired, and I will say that okay, just move here. So basically everything is using a system call. Let me know if that is clear to everyone. So that's called process state diagram. How many states I have here? 1, 2, 3, 4, 5. Right? I mean, this is not the only diagram that is possible. Like if you want, you can have any diagram. For example, maybe you can say I do not have only one block state. Maybe I do have multiple block state. Which means if it is sleep, then I will say okay, there is a block state that is just for the sleep. Okay, sleep block state. I mean, I'm just telling it. It is up to the design, right? I mean, you can have any process state diagram, but it is a typical scenario that happens in the operating systems, like Linux and all. Okay. Now there are two or three kind of schedulers which are called long-term scheduler, short-term scheduler, and one is called medium-term scheduler. First, let's look at this long-term and short-term scheduler. Long-term scheduler is basically a scheduler that does this loading up program, which means move a new, a fresh program and then make it a process. So it becomes a process here. So that job is done by long-term scheduler. Okay. So this job is done by long-term scheduler. And when it actually gets scheduled, that is done by this the scheduling, basically this cycle. Okay, this cycle is done by short-term scheduler, right? So this ready to running or running to ready is basically the short-term scheduler. Let me know if that is fine to everyone. Now suppose you have this diagram, then there is something called a swapping out the program. I mean, you can swap out some program from the main memory to the disk also. Okay. So if the program is running, then obviously from the running you will not swap out immediately. If the program is not running, maybe okay, program is terminated, that then also you will not swap out. In which situation you may swap out? Can anyone tell me from which state you can swap out this program to the disk? Can you swap out from the running? Obviously the program is running, you will not swap out. Maybe if it is blocked, then you will say that okay, maybe sometimes the program is blocked, then it is not useful to keep that in memory, so I will swap out in the disk. So swap out from the disk. That is called suspended. The program is suspended. I mean, you can just make one more state, suspended, or maybe some people call it block suspended. Okay, block suspended, right? I mean, you can move out to this block suspended, and then maybe if it is ready, if it is not running, then you can also move out to the disk. Okay, moving to the disk. That is called suspended, means moving to the disk. That is called ready suspended. Okay. I mean, that's not very much necessary, these two states. Otherwise, like I do have the 5 states only, but including these 2 states, I will say that there are total 7 states if you want. Okay, these 2 states are optional in the sense that if you want to swap out, then only you will swap out. Otherwise, let's suppose there is no facility of swapping out, then obviously how can you swap out, right? So if there is no facility of swapping out, you will not swap out. So this is just a swapping out to the disk. Now you can keep both of these states just a one state also, that will a 6 state, but generally we keep them as a different state, so that I get to know that okay, like it is from the ready or it is from the block. Because like suppose if I want to move it to the disk again, move it to the main memory again, then I will move it to the ready only, I will move it to the block only. Anyway, this is a typical diagram. Let's not worry about that 7 state diagram, but you can just focus on this 5 state diagram. Let me know if that is clear to everyone. Okay, great. So since this is clear, let me move further. Now, what is a long-term scheduler? It basically schedules schedule a new state to the ready state. What is short-term scheduler? That's ready to running or running to ready. That's called short-term scheduler. And there is also called medium-term scheduler. Okay, there is something called medium-term scheduler. What is this medium-term scheduler does? It basically swap out. I mean, if you are swapping out to the disk, then it is done by medium-term scheduler. Medium-term scheduler. Okay, this is done by medium-term scheduler. Anyway, this medium-term scheduler is optional in the sense that if you swap out, then only you will be having this medium-term scheduler. These are just names. Okay. See here, this is just a queue diagram. I mean, initially you are putting in the ready queue. Okay, I mean these are the jobs that you want to run, and this long-term scheduler is putting in the ready queue. This is the ready queue, and then the short-term scheduler is actually running on the processor, which is CPU, right? This is actually a CPU, and then this medium-term scheduler will do what? If let's from this ready, if I am going to the block, then that is from okay, this is ready suspended. Okay, so from this ready, if I am going to the suspended, that is done by the medium-term scheduler. If from this ready, I can also go to the block, right? Which is this, from this ready, sorry, not from this ready, from this running I can go to the block, and then from this block I can go to the block suspended. That is also done by the medium term scheduler. Okay, so anyway, like the diagram is this only, it was just using the queues. So from this ready you can go to the running, and then from this running you can go to the block, and then from this block you can you can swap out this, or maybe from this ready also you can swap out this, right? Okay, now I think it is a good idea to see some questions. You can see my screen, right? Let me know if everything is visible. Okay. So what they are saying, consider the following direct process state transitions. Direct, they have also defined what does this direct means. By direct, it means that the process can transition directly from first state to the second without passing through any intermediate state. Which means from this running to ready, is it possible to go from running to ready? That's what they are asking. This is a direct transition. Is the direct transition from running to ready is possible or not? What do you think? If it is running, then immediately can you switch out to ready? Yes, if that is a preemptive scheduling, right? If it is true, if preemptive scheduling, I mean they need to mention whether the scheduling is preemptive or not, but if I take it preemptive scheduling, then yes, true if preemptive scheduling. What about this? Ready and then immediately can it run? Yes. Ready, then can it get blocked? Yeah, that's interesting. If it is ready, then can it get blocked? Just think about it. If it is ready, then from this ready I will not get to know that what to run, right? I mean whether it is issuing some system call or it is issuing some IO or something, right? I will not get to know. I am not executing the process. So how can I move it to block without even executing it anything, right? To move it to block I need to do something, maybe the sleep, maybe some IO operation or something like this, right? Or maybe wait for the child in case of fork. So if it is I'm not even running it, then how can I move it to block? So that's false. Have you understood this? Let me know if that is okay to everyone. So Harish is saying 29 is no. Yes, that is true. So everyone understood why 29 is no, right? Okay. Now let's just see this. If it is block, then can it be ready? Yes, you can move it to ready. If it is running, then can you move it to blocked? Yes, because of some system calls. If it is blocked, then can you immediately run it? If it is blocked, this 32 is interesting. What about the 32? If it is blocked, then can you immediately? No, you need to first move it to ready, and then ready will move it to block running, right? So that is false. See, yes, no and no. So 29 and this 32 is no, right? Apart from this, everything is true. I hope you understood that question, right? Okay. Now let's just see this question. What they are saying: a preemptive scheduler is invoked on a OS. Is invoked when the currently running process finishes execution and terminates. A preemptive job scheduler is invoked when the currently running process is finished execution and terminates. Yeah, if it is going from running to terminate, then there should be some job scheduler that should move something from ready to running, right? Running. So a preemptive job scheduler, yes, I mean a preemptive can do from running to ready also, and obviously if it is a preemptive job scheduler, then you have to invoke it to move from ready to running also. That's why it is true. A currently running process issues a system call, blocking system call. If it is running, if it is issuing a block system call, then it will go to the block. That is fine. But are you running a job scheduler here, obviously like you need to run something, right? I mean, the question might not be very much well framed, but assuming that you always have something to run, then this ready to running will also be there. That way it is true. Another process I use complete, moving that process to ready queue. Okay, I mean, if you're moving from block to ready, then do you run a job scheduler here? What do you think? Another process IO is complete, which means the currently running process IO is not complete, and another process IO is complete, moving that process to the ready queue. If you're moving that process to the ready queue and currently there might be running something, then do you need a job scheduler here? The timer interrupt occurs, the time quantum exceeds. So yes, here I will be needing a job scheduler, but here I don't think we need a job scheduler, right? Because if you are running, if you are moving some process to block to ready, then you are not scheduling anything essentially, right? So that's why it should be false. Let me know if you got it, right? Okay, so this should be false, that is wrongly printed. Okay, let's move further. Now let's see what they are asking. I hope my screen is visible to everyone. Let me just pull it little down. Okay, so what they are asking is this, that with regard to the scheduling, indicate into which category of scheduling, if any, of these activity listed below false. Okay, so dispatching means scheduling or something, scheduling a kernel level thread to the CPU. Who does this? Kernel level thread to the CPU. What do you think? Who does this? Long term, medium term, short term? All, more than one? I think the long like short term only, right? So short term scheduler schedule any thread to the I mean any process to the CPU. It may be the kernel thread, it may be a user thread also. I mean it will schedule a process. If the process is having the user level thread, then also it will do it, right? It basically schedule a process. A user, if you want to schedule a user level thread to the CPU, then only this short term scheduling will do it, because for the short term scheduling it is just a process, it is scheduling a process. In that inside that process, whatever you have, it is up to you. I mean, if you want to schedule this particular user level thread, that's up to you. Up to you means up to the user. Dispatching or scheduling of a process to the CPU, or yeah, if it is even the process, then it is a short term scheduler. Swapping out a process from main memory to the disk, or out of the main memory to the disk, swapping in or swapping out, so that is done by the medium term scheduler, so that way it is B. Admission of the process to the system, which means from new to ready. Who does this? That is done by long term scheduler, right? So that's why A is the correct answer here. Yeah, CCCBA. Okay. So let's just see this question. Maybe this is one of the last question that I have, and then we will be solving some gate PYQs, right? Okay. So I hope the question is visible to everyone. What do you think about the each option? Please let me know. A kernel implements all of the functionality of the operating system. Okay. So I mean, these are some subjective questions that are actually, this is not required for us, so that's why I'm removing this. This one, two, these are not required. Okay. Just a second. Sorry. Let's just start from this 6. What they're saying, that in a multi-threaded processing, With the kernel level threads, various threads associated with the single process must share the common thread state. Okay, I think we did it right. So kernel level threads do not share the common thread state, so that's why it is false. In all operating systems, a new program can be loaded into the child's memory address space at the instance of initial creation of the child process, different from the program in the parent's memory address space if it is desired that the child process execute a different program than the parent. Okay, just tell me if it is true or false. It is asking something about the fork exec. In all operating system, a new program can be loaded into the child process memory address space at the instant of the initial creation of the child process. So initially you can load that new program into the child memory address space, different from the program in the program's parent's memory address space, which means it is completely a new program. If it is desired that the child process execute a different program than the parent. See, this last line is very crucial. They are saying if it is desired that the child process execute a different program than the parent. If the child is, see, if the parent is this and the child is as it is copy of the parent, then I can destroy this child, right? And I can load something using the exec. That's what I can definitely do. But they are saying I want this child to do something else. Then obviously there is no point in destroying this child, right? If I want child to do something else, then there is no point in destroying this child. So that is why this is false. Okay. Because the last line is saying if it is desired that the child process execute a different program than the parent. So if that is desired, then I will say this is false. For the kernel level threads, when one thread associated with a particular process becomes blocked, then the entire process is blocked. So this is also false, because for the kernel level thread that's not the true. Kernel is a part of operating system that run continuously. Okay, these are basically bit specific details about the implementation, so that's why I'm removing it. Let's just see this 11. A midterm scheduler must be a part of every operating system other than those execute a single task at a time. So midterm scheduler is what? Swapping out and swapping in. So they are saying it must be a part of every operating system. What do you think? As I said, it was optional, right? If you remember, I said midterm scheduler is optional thing, right? It is optional. It need not to be a part of every operating system. So that is why this is false. A multi-threaded programming, a various in a multi-threaded programming, multi-threaded means there are multiple threads. The various threads associated with the single process share a common user stack. Do they share a common user stack? Answer is false, right? I think we did all of this. Okay. Now let's just do some gate PYQs related to the scheduling. In the following process state diagram, for the uniprocessor system, which means there is only single CPU, okay, assume that there are always some process that are in the ready state. So there are always some process that I want to run. Now consider the following statement. If the process make a transition D, which means the process, it would result in the another process making a transition A immediately. Is this true or false? If there is always something, then it is true or false? If a process make a transition D, then do you always make a transition which is A, which means you always load a new process? No, right? I mean there might be a process in the ready state, but there might not be a new process always. So that's why it is false. If it could have been B, then it is true. Why? Because B is saying that that you always have something to move here, right? So that's why it is true. If something is finished, then you will move something. But if it is A, then it is false. A process P2 is blocked state can make a transition E. Okay, in a blocked state can make a transition E, while the another process P1 is in the running state. Yeah, that is true. I mean, another process, something is running, CPU is busy in this, and then the block is completed, then you can schedule it to the ready state. The OS uses preemptive scheduling. Okay, this kind of OS is using preemptive or non-preemptive. Because of the C, that's why it is using the preemptive scheduling, right? Because of C. Because of C. So that's why second and third is answer, right? So C is answer, which is second and third. Okay. Now let's move to this. Consider the following statement about the process state diagram for the system using the preemptive scheduling. A running process can move to the ready state. A running process can move to the ready state. If it is using preemptive scheduling, then yes. A ready process can move to the running state. This question has been asking very recently. A ready process can move to the running state. If it is ready, then yeah, it can move to the running state. A block process can move to the running state. No, that is false. A block will move to the ready and then it can move to the running. Can move to the ready state. Yes. So third is false. Apart from this, everything is true. So that will be C is answer. Yes. So answer is C, right? So I think that is enough for today. And tomorrow we will be starting the scheduling, which is first come first serve, right? FCFS. Shortest job first, these kind of scheduling, round robin, right? This kind of scheduling we will be starting tomorrow. Starting means like we will be doing some questions for this scheduling. Let me know how you want to proceed these sessions, which means should I not recap the theory or should I directly go with the questions? Should I only solving the gate PYQs? And I mean, how I should be proceeding? Should I be recapping the theory more quickly than I'm currently recapping? Should I not be spending time in theory? So let me know like how you want to proceed with these sessions and we will take your feedback, then we will go like that, right? So just comment it out. Okay, whatever your suggestion, please comment your suggestion, how you want to do it. Okay. Thank you everyone. Take care. Bye bye.